Max, a math major, is studying in his apartment. His Wi-Fi keeps dropping, so he walks around with his phone, searching for a stronger signal. At first, this might seem obvious, just move closer to the router. But Max has a problem. The router is shared with his friend John, who lives one floor below him. John is away for several days, so Max cannot ask where the router is. From Max's floor, the router is hidden. His phone shows one signal strength number at his current location, but one number does not tell him which direction to walk. Now imagine the invisible Wi-Fi signal as a contour map through the apartment. Each contour connects points with the same signal strength. The label f of x, y, z reminds us that the full signal depends on position in 3 dimensions. If Max could see this map, he could move from weaker contours toward stronger ones. But he cannot see the function. He only measures where he checks. So here is the question: from Max's current location, where should he move next? North, south, east, west, or somewhere in between? This is exactly the question the gradient answers. A scalar value tells how strong the signal is. The gradient turns nearby changes in that value into a direction, the direction of fastest increase. There is one more important constraint. The real signal field lives in 3 dimensions, f of x, y, and z, because the router is below Max. But Max can only walk on his apartment floor, where z is fixed. So his search happens on a 2-dimensional slice, f of x and y equals f of x, y, z0. Dead zones and local maxima can still appear on that slice. Let us use mathematics to understand Max's situation. Max is studying, and suddenly the Wi-Fi becomes weak. His phone shows one number for the Wi-Fi signal strength at his current location. In Wi-Fi, signal strength is shown with negative values, so a value closer to 0 is stronger. For example, minus 58 dBm is better than minus 72 dBm. When Max tries to walk a little, the signal drops. One number on his Wi-Fi analyzer does not tell him which direction to walk. So he starts moving around. At each position, he gets a new Wi-Fi strength value. Each step on his floor gives him another measurement. But he is not aware of the hidden contour map of the function. He only knows the signal strength at the places where he has actually checked. Now let us describe this mathematically. The real Wi-Fi signal is a 3-dimensional field, f of x, y, and z. But Max can only walk on his apartment floor, so z is fixed. On that floor, we study a 2-dimensional slice, f of x and y equals f of x, y, z0. The goal is to find where this slice has the largest value. That means the strongest Wi-Fi signal Max can reach. If we could see the hidden Wi-Fi field, it would look like a contour map. Each contour connects places with the same signal strength. Moving along one contour keeps the signal almost the same. To improve the signal, we need to move from a weaker contour to a stronger contour. On a contour map, the gradient points across the contour lines. More precisely, when grad f is not 0, it is perpendicular to the contour through that point. Of the 2 perpendicular directions, grad f chooses the side where f increases. For Wi-Fi, that means stronger signal. So if we had the full map, following grad f would move us from weaker signal regions toward a local maximum. But in real life, Max does not know the full function. He does not see the contour map. So he estimates the gradient by checking nearby points. If the signal is stronger to the east and slightly stronger to the north, then the gradient points mostly east and slightly north. That direction is his best local guess. Mathematically, the gradient is made of partial derivatives. In 2 dimensions, since Max can only move on his apartment floor, grad f equals partial f by partial x, partial f by partial y. The first part tells how fast the signal changes in the x direction. The second part tells how fast the signal changes in the y direction. Together, they form the gradient arrow, grad f. Now choose a walking direction and call it u, where u is a unit vector. The directional derivative, grad f dot u, tells us how much the signal changes per small step in direction u. This value is largest when u points in the same direction as grad f. If u points sideways, the change is smaller. If u points opposite, the signal gets worse. That is why gradient ascent moves in the gradient direction. Gradient ascent uses this rule. New position equals old position plus step size times the gradient. The step size controls how far we move. We do not jump all the way. We take a small step, because the best direction can change after we move. Then we repeat. Measure the signal. Estimate the gradient. Move a small step. Measure again. Each step should move us toward stronger Wi-Fi, until the signal stops improving much. At that point, we are near a local maximum. So gradient ascent is not magic. It is a repeated search process. You look at how the value changes nearby, find the direction of fastest increase, move a little in that direction, and repeat. Next time you walk around trying to find better Wi-Fi, your brain is doing a rough version of gradient ascent. Let us summarize what we learned. Max is not just wandering randomly. He is moving through a signal strength field. At any point, the Wi-Fi strength is a scalar value. Contour lines show equal signal strength, and the gradient at a point is perpendicular to the contour through that point. Following the gradient means taking a small step toward the fastest local increase. Then we measure again, update the direction, and repeat. That repeated process is gradient ascent. The big idea is simple. Gradient ascent turns local measurements into a direction, and that direction points toward stronger Wi-Fi.